Good evening. Tonight we will travel back to a world cloaked in darkness. Before the glow of city lights, before the hum of refrigerators in quiet kitchens, before the gentle flicker of a television illuminating a darkened room, the world moved at a slower pace. Night arrived, and with it came darkness. The setting sun marked the end of the day for most people. Streets became shadows, homes gathered around small pools of candlelight, and the quiet sounds of the evening settled over villages and cities alike. A person living hundreds of years ago would have recognized the rhythm of the world in a way that feels almost unfamiliar today. Work followed the rising and setting of the sun. Travel became more difficult after nightfall. The darkness was not something to be pushed away, but something to be accepted. Yet hidden all around them was a force that would one day transform nearly every part of human existence. It was invisible. It had no shape, no color, and no sound of its own. It flowed silently through the world, resting inside clouds, moving through certain materials, and waiting to be discovered. It could appear suddenly as a spark between two objects, or burst violently from the sky as a flash of lightning stretching across the horizon. This mysterious force was electricity. Today, electricity feels ordinary. We flip a switch, and a room fills with light. We plug in a device, and energy flows quietly into it. We wake up to alarms, communicate across oceans, preserve food, heat our homes, and explore space using the power of electrical currents. But electricity was not always understood. For most of human history, it was a mystery. Ancient people watched lightning storms with a mixture of fear and wonder, seeing enormous flashes of light tear across the sky without knowing what caused them. They saw sparks jump from objects and felt strange sensations from certain materials, but they had no idea they were witnessing the early clues of one of nature's greatest secrets. The story of electricity is not the story of one invention or one brilliant individual. It is a long journey stretching across thousands of years. It is the story of curious minds observing the natural world, asking simple questions, and slowly uncovering the invisible forces surrounding them. It begins with a piece of amber rubbed against cloth. It continues through candlelit laboratories where early scientists created tiny sparks and tried to understand their strange behavior. It passes through thunderstorms, where researchers risked their lives trying to prove that lightning itself was electrical. It travels through quiet workshops where inventors built the first batteries, generators, motors, and communication devices. And eventually, it reaches the glowing streets of modern cities, where electricity became the foundation of the world we know today. The journey was slow. There were failures, disagreements, and countless experiments that led nowhere. Many discoveries came not from grand moments of inspiration, but from patient observation. A scientist noticing a needle move slightly. An inventor watching a spark jump between two objects. A researcher spending years testing ideas that seemed impossible. The history of electricity is, in many ways, a history of human curiosity. It is a story of people trying to understand something they could not see. Long before power lines stretched across landscapes and towering electrical plants supplied energy to millions of homes, electricity existed quietly in nature. It was present in every storm cloud, every flash of lightning, and every tiny spark created by friction. Humanity did not create electricity. Instead, humanity slowly learned how to recognize it, control it, and eventually build an entire civilization around it. The arrival of electricity changed the world more dramatically than many of the greatest inventions in history. It changed how cities looked. It changed how people worked. It changed how families spent their evenings. It changed how information traveled. It changed the very rhythm of daily life. A person from the year 1700 stepping into a modern city would find it almost impossible to understand. Buildings glowing through the night. vehicles powered by invisible energy, messages traveling instantly across the planet, machines performing tasks that once required the strength of hundreds of people. All of it made possible by the movement of tiny particles that humans cannot see. And yet, despite its incredible importance, electricity has become something we rarely think about. It is always there, waiting behind walls, moving beneath streets, flowing through wires, quietly powering the world. Tonight, we will follow the long and fascinating journey of this invisible force. We will travel from ancient observations of static sparks to the laboratories of the great electrical pioneers. We will watch cities transform as electric lights replace gas lamps, and we will explore the inventions that brought electricity from scientific curiosity into every corner of everyday life. We will meet the thinkers who helped reveal electricity's secrets, from early philosophers studying mysterious materials to inventors who dreamed of a world illuminated by artificial light. We will walk through the first electrically powered streets. We will listen to the quiet tapping of telegraph machines sending messages across continents. We will step inside homes experiencing electric appliances for the first time. And we will eventually arrive in the modern world, where electricity has become the invisible foundation beneath nearly everything we do. So, settle in, let the room grow quiet, and imagine a time before the simple comfort of turning on a light. Imagine a world waiting in darkness, unaware of the incredible force hidden all around it. A world filled with questions. A world filled with curiosity. A world waiting to discover electricity. Long before electric lights illuminated cities, before power lines stretched across continents, and before the quiet hum of machines filled our homes, humanity lived in a world shaped by a very different kind of energy. A world of fire. For thousands of years, the rhythm of human life was guided by the rising and setting of the sun. Morning arrived with the first rays of daylight, bringing people out into fields, workshops, and streets. Evening arrived slowly, as the sky faded from blue to orange, and finally into the deep darkness of night. The darkness was not something unusual. It was simply part of life. When the sun disappeared beyond the horizon, people relied on small flames to extend their days. A simple candle could provide enough light for a person to read, write, or complete a small task. An oil lamp could brighten a room. A fireplace could warm a home and bring families together during long winter evenings. But these sources of light were limited. A candle burned only as long as the wax remained. An oil lamp required constant fuel. A fire needed wood to be gathered, carried, and carefully maintained. Every bit of warmth and light required effort. The modern idea of simply pressing a button and filling an entire room with brightness would have seemed almost magical. Yet even in this world illuminated by fire, people were surrounded by electricity. They just did not know it. Electricity had always existed in nature. It flowed through storms, rested within certain materials, and appeared suddenly in flashes and sparks. It was present in the world long before humans had names for it or understood how it worked. The earliest encounters with electricity were not made in laboratories. They happened in ordinary moments. A person rubbing a piece of amber against cloth and noticing that it attracted small pieces of dust. A traveler watching lightning split across a dark sky. A sailor observing strange glowing lights appearing around the mast of a ship during a storm. To ancient people, these events were mysterious signs of nature's power. Lightning was often viewed as something divine, a force connected to gods and the heavens. The sudden brightness of a storm, followed by the tremendous sound of thunder, seemed beyond human understanding. Across many cultures, lightning became associated with powerful beings. The ancient Greeks believed lightning was connected to Zeus, the ruler of the gods, who carried a thunderbolt as a symbol of his authority. The Norse told stories of Thor, whose hammer created thunder and lightning as he traveled across the sky. Many other civilizations developed their own explanations for storms and flashes of light from above. These interpretations were not simply stories. They were humanity's earliest attempts to explain something extraordinary. People were observing the natural world and trying to understand forces that seemed impossible to control. Among the earliest recorded observations of electricity came from the ancient Greek philosopher Thales of Miletus, who lived more than 2,500 years ago. Thales noticed that when amber, a fossilized tree resin, was rubbed with cloth, it could attract small objects such as feathers or pieces of straw. The Greeks called amber electron. From this word would eventually come the modern term electricity. At the time, however, this strange attraction was simply a curiosity. There was no understanding of atoms, charges, currents, or invisible particles. There was only observation. Something unusual happened when certain materials interacted. That was enough to inspire curiosity. 4 centuries afterward, electricity remained mostly a mystery. People noticed strange effects, but they did not yet have the tools or knowledge needed to study them deeply. The world continued on without electrical technology. Cities grew, civilizations rose and fell, and human creativity found countless ways to solve problems without electricity. Architects designed magnificent buildings using stone and wood. Engineers created roads, bridges, and ships. Farmers developed new methods of growing food. Artists painted masterpieces by candlelight. Human civilization was not stagnant. It was simply powered differently. Energy came from human hands, animals, wind, water, and fire. A farmer relied on the strength of horses and oxen. A blacksmith relied on the heat of a furnace. A sailor depended on wind filling the sails of a ship. A family depended on a carefully tended fire to survive the winter. The idea that invisible energy could travel through wires and operate machines was almost unimaginable. The closest people came to experiencing electricity were rare natural events. Imagine standing outside on a warm evening centuries ago, watching a storm approach from the horizon. The air becomes heavy. The clouds grow dark. The wind begins to move through the trees. Then suddenly, the sky flashes. For a brief moment, the entire landscape is illuminated. Mountains, fields, and forests appear as if daylight has returned for a fraction of a second. Then darkness returns. A moment later comes the thunder, echoing across the land. To someone living in the ancient world, lightning was one of nature's greatest mysteries. It was powerful, unpredictable, and impossible to capture. But hidden within that flash was the same force that would eventually power cities, computers, and spacecraft. The journey from lightning in the sky to electricity flowing through homes would take thousands of years. It would require countless experiments, discoveries, and moments of unexpected insight. But before electricity could transform civilization, humans first had to recognize that the strange sparks and flashes they witnessed were not separate mysteries. They were connected. The same force that created lightning storms could also appear in a small spark from a piece of amber. The same energy that seemed to belong only to the heavens could eventually be brought into human hands. For now, though, electricity remained a quiet secret of nature. The world continued to sleep beneath skies filled with stars. Homes glowed softly with candlelight. Fires crackled in hearths. And somewhere in the darkness, hidden within the natural world, was an invisible force waiting to be discovered. The age of electricity had not yet begun, but the first questions had already been asked. 4 centuries after the first observations of amber and its mysterious attraction, electricity remained a quiet curiosity. It was something people noticed, but did not understand. A strange little force that appeared under very specific circumstances. A spark created when two materials touched. A tiny attraction between objects. A sudden shock felt on the skin after walking across a floor. The invisible force that would eventually power entire cities was already revealing itself in small, almost ordinary ways. During the Renaissance period in Europe, curiosity about the natural world began to grow. Scholars, philosophers, and experimenters started looking beyond ancient explanations and began testing ideas through observation and experimentation. One of the first people to seriously study electrical phenomena was an English physician and scientist named William Gilbert. Living during the late 1500s and early 1600s, Gilbert was fascinated by magnetism and the strange forces that could act without physical contact. At the time, magnets themselves were still mysterious objects. A piece of iron could move toward another object without anything visibly pushing or pulling it. Gilbert wanted to understand these invisible forces. Through careful experiments, he studied how materials behaved when rubbed together. He discovered that amber was not unique. Many other materials could produce similar effects. Glass, sulfur, wax, and other substances could become electrically charged when rubbed. Gilbert introduced the term electricus to describe this phenomenon, based on the ancient Greek word for amber, electron. This was an important moment. For the first time, electricity was being recognized as a natural force worthy of scientific study. However, electricity was still far from something useful. There were no machines powered by electrical energy, no wires carrying currents, no lights glowing in homes. Electricity was more like a fascinating trick performed in quiet rooms. Scientists could create it, observe it, and demonstrate it, but they had no way to control it for practical purposes. One of the most popular tools for studying electricity was the electrostatic generator. These early machines were simple but fascinating. A person would turn a handle that rotated a glass sphere or cylinder, creating friction between materials. As the machine moved, it produced a build-up of electrical charge. The result was often dramatic. A scientist could touch the machine and produce a spark. Small objects could be attracted or repelled. A person's hair might stand on end as electrical charges moved across their body. To audiences watching these demonstrations, electricity seemed almost alive. In the 1700s, public electrical demonstrations became a form of entertainment as well as science. Lecturers traveled from city to city, showing crowds the strange effects of this invisible force. People gathered in theaters and lecture halls to watch sparks fly and experiments unfold. Some demonstrations were playful. A person might be connected to an electrical machine and produce sparks from their fingertips. Others involved chains of people holding hands and receiving a small electrical shock together. These events were sometimes called electrical amusements. But beneath the entertainment was a growing scientific interest. Researchers were beginning to realize that electricity was not just a strange attraction between objects. It seemed to follow patterns. It could be stored. It could move. It could be transferred. The mystery was slowly becoming a science. One of the most important inventions of this period was the Leyden jar, created in the mid-1700s. Before the Leyden jar, scientists could generate electricity, but they struggled to store it. The electrical charge disappeared almost immediately. The Leyden jar changed that. It became one of the first devices capable of storing electrical energy. The invention was relatively simple: a glass container with conductive materials placed inside and outside. When connected to an electrical source, the jar could hold a charge. Then, when discharged, it released that energy suddenly. A flash, a spark. A shuck. The Leyden jar amazed scientists because it showed that electricity could be captured and saved for later use. For the first time, electricity was not just a momentary event. This discovery opened new possibilities. Scientists began experimenting with larger and more powerful electrical machines. They wanted to understand how electricity moved and what rules governed its behavior. One of the most famous experimenters of this period was Stephen Gray, an English scientist who discovered that electricity could travel through certain materials. Through his experiments, Gray found that some substances allowed electrical charge to move easily, while others resisted it. Although the concepts of conductors and insulators would not be fully understood for many years, these experiments provided an important clue. Electricity could move. And if electricity could move, perhaps one day it could be directed. This idea would become one of the foundations of modern technology. Scientists developed different theories, and debates continued. Some believed electricity was a single type of energy that could flow between objects. Others believed there were different types of electrical charges interacting with one another. The study of electricity required patience because the force itself was invisible. Scientists could only observe its effects. They could see sparks. They could measure movement. They could watch objects attract or repel. But the actual nature of electricity remained hidden. In many ways, studying electricity was like trying to understand the wind before anyone knew what air was. You could see the leaves move. You could feel the breeze. You could watch storms arrive. But the thing itself remained unseen. Yet every experiment brought humanity closer. The small sparks created in Renaissance laboratories were the first steps toward a world powered by electricity. The glass spheres, metal rods, and early machines may have seemed like simple curiosities, but they represented something much greater. They were humanity's first attempts to reach into the invisible, to understand a force that had always existed, to take something found in lightning storms and hidden within ordinary materials and slowly bring it under human control. The age of electricity was still far away, but the first sparks had appeared. For thousands of years, lightning had been one of nature's greatest mysteries. To early civilizations, lightning was a force beyond human control. It was powerful, it was unpredictable, and it seemed to come directly from the heavens. But by the 18th century, a new way of thinking had begun to spread. Scientists were no longer satisfied with simply accepting mysteries. They wanted to understand them. They wanted to measure the natural world. They wanted to recreate its wonders in laboratories. And one of the greatest questions of the age was whether the strange sparks produced by electrical experiments were somehow connected to the enormous flashes of lightning that crossed the sky. Could the tiny sparks created by machines and the massive energy of storms actually be the same force? The answer would come from one of the most famous experiments in scientific history. It would involve a stormy sky, a simple kite, and a curious mind named Benjamin Franklin. Benjamin Franklin was born in Boston in 1706, during a time when electricity was still largely unknown. He became known for many things throughout his life: a writer, printer, inventor, statesman, and philosopher. But long before he helped shape the future of the United States, Franklin was fascinated by science. Like many thinkers of his time, he was captivated by the growing field of electricity. Scientists could create sparks, charge objects, and produce dramatic effects with electrical machines. Franklin was not interested only in the spectacle. He wanted to understand what was happening. In his Philadelphia home and workshop, Franklin began conducting his own experiments with electricity. He studied electrical charges and developed ideas about how electricity behaved. At the time, Many scientists believed electricity was a kind of invisible fluid that could move between objects. Franklin proposed that there were two types of electrical states, positive and negative. While our modern understanding of electricity is more complex, Franklin's ideas helped create a foundation for future electrical science. But his greatest question remained: was lightning itself electrical? The idea may seem obvious today, but in the 18th century it was still a matter of debate. A small spark from a glass tube and a bolt of lightning stretching across the sky seemed like completely different things. Franklin believed they were connected. To prove his idea, he needed a way to bring electricity from the sky down to Earth. This led to one of the most famous experiments ever performed. During a thunderstorm in 1752, Franklin and his son William went outside with a kite made of silk. Attached to the kite string was a metal key. The purpose was not to capture lightning directly, as the story is sometimes told, but to observe whether electrical charges from the storm clouds could travel down the string. As the storm approached, the kite rose into the dark sky. The wet string carried electrical charge from the atmosphere. When Franklin moved his hand near the metal key, he noticed that tiny sparks appeared. The electricity of the storm could be detected. The invisible force in the clouds was the same force scientists had been studying in their laboratories. Lightning was electrical. The discovery was enormous. It connected two worlds that had previously seemed separate. The mysterious flashes above the clouds and the tiny sparks created by human hands were revealed to be part of the same natural phenomenon. Franklin had taken one of nature's most frightening mysteries and brought it into the realm of science. However, the experiment was not without danger. Lightning carries an incredible amount of energy, and attempting to capture it directly could have been deadly. Another researcher, George Wilhelm Richman of Russia, was killed while attempting electrical experiments during a storm shortly after Franklin's discovery became known. The danger of electricity was becoming clear. This force was fascinating, but it was also powerful. Understanding electricity meant learning how to respect it. Franklin's discoveries led to one of his most practical inventions, the lightning rod. Before lightning rods existed, thunderstorms posed a serious threat to buildings. Tall structures, especially churches and homes with wooden roofs, were vulnerable to lightning strikes. A single strike could ignite a fire and destroy an entire building. Franklin's lightning rod provided a simple solution. A metal rod placed on top of a building would attract the electrical discharge from a lightning strike and safely direct it into the ground through a conductor. It did not stop lightning. Instead, it gave lightning a safer path to follow. The invention spread quickly and became one of the first practical uses of electrical knowledge. For many people, the lightning rod was their first experience with electricity as something useful rather than simply mysterious. It represented a turning point. Electricity was no longer only a curiosity found in experiments and demonstrations. It was becoming something that could improve everyday life. Franklin's work also changed the way people viewed nature itself. The thunderstorm was no longer only a symbol of divine power or an uncontrollable force. It was a natural event governed by physical laws that humans could study and understand. This idea was part of a larger movement during the Enlightenment, an era when thinkers across Europe and America believed that reason, observation, and science could reveal the secrets of the world. Electricity became one of the greatest examples of this belief. Something invisible could be measured. Something mysterious could be explained. Something terrifying could become useful. Yet Franklin's discoveries were only the beginning. Knowing that lightning and electricity were connected raised even more questions. If electricity existed in storms, could humans create larger amounts of it? Could it be stored? Could it be controlled? Could it somehow be used to perform work? The answers would require many more experiments and many more discoveries. The spark created by a simple kite experiment would eventually lead to batteries, motors, communication systems, and the electrical networks that power the modern world. But for now, humanity had taken an important step. The heavens had revealed one of their secrets. The lightning in the sky and the spark in the laboratory were one and the same. Electricity was no longer just a strange force. It was becoming a science. After Benjamin Franklin revealed that lightning and electricity were connected, the mysterious force that had fascinated humanity for centuries began to enter a new era. Electricity was no longer only a strange curiosity. It was becoming a field of science. Across Europe and the Americas, laboratories became places of discovery. Scientists built new machines, developed new experiments, and searched for answers to questions that had fascinated people for generations. The answers would not come quickly. Electricity was unlike anything scientists had studied before. It could not be seen directly. It left behind clues but remained hidden itself. Researchers had to learn about it indirectly, through sparks, movements, and reactions. Every experiment was like a conversation with nature. A scientist would ask a question by building a device or changing a material, and electricity would answer through its behavior. Slowly, the rules of this invisible force began to emerge. During the 18th century, electrical demonstrations became increasingly popular. Wealthy households, universities, and scientific societies hosted gatherings where people watched researchers create sparks and shocks using newly invented machines. Guests gathered in elegant rooms illuminated by candlelight, watching with fascination as scientists produced effects that seemed almost magical. To many observers, electricity seemed like a glimpse into the hidden forces of nature. One of the most famous electrical experimenters of this era was the French scientist Charles-François de Cisterneuil-Dufay. In the 1730s, Dufay studied electrical charges and noticed that electricity seemed to behave in different ways. Some charged objects attracted each other, while others pushed apart. His experiments suggested that there were two different types of electrical behavior. This was an important step toward understanding electrical charges. Although scientists at the time did not yet know about electrons or atomic structures, they were beginning to recognize that electricity followed patterns. Another important figure during this period was Jean-Antoine Nollet, a French clergyman and physicist who became famous for his electrical demonstrations. Nollet helped popularize the study of electricity by creating dramatic experiments for large audiences. One of his famous demonstrations involved a group of people standing in a circle while holding hands. When an electrical charge was released, everyone in the chain would feel a sudden shock at nearly the same moment. The experiment showed that electricity could travel quickly through certain materials and across connected objects. To audiences, it was astonishing. A force they could not see could move through an entire group of people. Electricity seemed almost alive. But these demonstrations also revealed something important. Electricity was not simply a strange attraction between objects. It could be transferred. The next challenge was learning how. As experiments became more advanced, scientists began building larger electrical machines. One of these was the friction generator, which used mechanical movement to create electrical charges. A person would turn a handle, causing materials to rub together and produce static electricity. These machines became more powerful over time. Some could generate impressive sparks that stretched several inches through the air. The sparks were beautiful, but they also revealed electricity's danger. Researchers learned that electrical energy could cause painful shocks, burns, and even death. The same force that created fascinating displays could also be destructive. This combination of beauty and danger made electricity even more intriguing. It was something that needed to be understood before it could ever be controlled. One of the most important discoveries of the 18th century came from experiments involving electricity and the human body. Scientists noticed that living things could conduct electrical charges. They experimented with animals, plants, and eventually human subjects. These experiments were often strange by modern standards, but they reflected the excitement surrounding a force that seemed capable of interacting with life itself. Some researchers began wondering whether electricity might be connected to the body's own functions. Could the signals that moved through nerves be electrical? Could electricity explain movement, sensation, or even thought? Although these ideas were far ahead of what science could prove at the time, they showed how deeply electricity had captured human imagination. The study of electricity was spreading beyond physics. It was becoming connected to medicine, biology, chemistry, and engineering. The growing interest in electricity also led to the creation of scientific societies dedicated to sharing discoveries. Researchers across different countries exchanged letters, drawings, and descriptions of experiments. A discovery made in one city could inspire a new experiment thousands of miles away. Science became a global conversation. The invisible force of electricity was bringing people together long before it would eventually connect the world through technology. By the late 18th century, electricity had moved from a strange observation about amber and sparks into a serious scientific discipline. The basic ideas were beginning to form. Electricity could be generated. Electricity could be stored. Electricity could travel. But there was still one major problem. Electricity created by friction machines was temporary. A scientist could build up a charge and release it, creating a brief spark or shock. But once the energy was gone, the experiment had to begin again. There was no continuous source of electricity, no steady flow, no electrical current that could be maintained. The dream of practical electricity remained distant. Scientists needed a way to produce electricity whenever they wanted, not just in short bursts. They needed a device that could provide a reliable supply of electrical energy. The next great breakthrough would come from an unexpected place. Not from lightning, not from a spinning machine, but from chemistry. By combining different materials and studying the reactions between them, scientists would discover a way to create a steady electrical current. This invention would change everything. For the first time, electricity would no longer exist only as a brief spark. It would become a flowing force, a force that could be studied, measured, and eventually used to power the modern world. The age of experiments had begun. For much of human history, electricity had existed only in brief moments. A spark from a piece of amber, a flash from a glass generator, a shock from a Leyden jar. These events were fascinating, but they were temporary. Electricity appeared suddenly and disappeared just as quickly. Scientists could create it. They could observe it. They could store small amounts of it. But they could not produce a steady, reliable flow. The dream of practical electricity remained just beyond reach. To transform electricity from a scientific curiosity into a powerful tool, researchers needed something completely new. They needed a source of continuous electrical energy. They needed a way to create electricity on demand. The breakthrough would not come from lightning or friction machines. It would come from chemistry. In the late 18th century, a quiet revolution was beginning in the world of science. Researchers were discovering that different materials could interact in surprising ways. Metals, liquids, and chemical reactions were revealing hidden connections between chemistry and electricity. Among those studying these connections was an Italian scientist named Luigi Galvani. Galvani was a physician and professor of anatomy at the University of Bologna. His work focused primarily on the human body, especially the nervous system and the relationship between muscles and movement. In the 1780s, while conducting experiments with frogs, Galvani noticed something unusual. During one experiment, he observed that the legs of a dead frog twitched when they were connected to certain metals. The movement seemed almost impossible. The frog was no longer alive, yet its muscles responded as if they had received a signal. Galvani believed he had discovered a form of electricity produced by living creatures. He called it animal electricity. His experiments suggested that electricity might be connected to life itself. The idea captured the imagination of scientists across Europe. But another researcher had a different interpretation. His name was Alessandro Volta. Volta, a professor of experimental physics at the University of Pavia, was fascinated by Galvani's work. However, he questioned whether the electricity was truly coming from the animal tissues. Instead, Volta believed the source was the metals themselves. He suspected that when two different metals touched each other in the presence of moisture, they created an electrical reaction. This disagreement between Galvani and Volta led to years of experiments. Rather than simply debating ideas, Volta began carefully testing different combinations of materials. He used various metals, liquids, and conductors, searching for a way to create a continuous electrical effect. Eventually, he discovered something remarkable. By stacking alternating layers of zinc and copper, separated by pieces of cloth soaked in salt water, he could produce a steady flow of electricity. This device became known as the voltaic pile. The first true battery had been created. It was a simple invention, but its importance was enormous. For the first time in history, humans had a device capable of producing a continuous electrical current. Electricity was no longer limited to brief sparks and stored charges. It could flow. It could be measured. It could be used in experiments that were impossible before. The voltaic pile changed the direction of electrical science almost overnight. Scientists who had previously relied on static electricity machines now had access to a new kind of power. Instead of generating electricity through friction, they could create it through chemical reactions. This opened an entirely new world of possibilities. One of the first major discoveries made possible by the battery was the ability to separate chemical compounds using electricity. In the early 1800s, English scientists William Nicholson and Anthony Carlisle used a voltaic pile to perform electrolysis, breaking water into hydrogen and oxygen gases. This was a remarkable demonstration. Electricity could cause chemical changes. It was not just a strange force of attraction or a flash of energy. It could actively transform matter. The battery had revealed that electricity and chemistry were deeply connected. Around the same time, other scientists began exploring the power of the voltaic pile. Humphrey Davy, a talented British chemist, used powerful batteries to conduct experiments that eventually led to the discovery of several new elements, including sodium and potassium. His work showed that electricity could unlock secrets hidden within ordinary materials. The invisible force was becoming a tool for discovery. The invention of the battery also changed the way scientists thought about electricity itself. Before the voltaic pile, electricity was often viewed as something that happened suddenly. A spark, a flash, a discharge. The battery introduced a new concept, current, a continuous movement of electrical energy. This idea would become the foundation for nearly every electrical technology that followed. The difference between a spark from an electrostatic machine and electricity from a battery was like the difference between a single drop of water and a flowing river. One was a brief event. The other was a steady source of power. The world had taken an important step toward the electrical age. Although the early batteries were limited, they were not practical for powering homes or machines. But their importance was not measured by what they could do immediately. Their importance was that they proved electricity could be created and controlled. Scientists now had a dependable source of electrical current, and they could begin asking new questions. Could electricity create movement? Could it produce light? The battery became the foundation for a new generation of experiments. It allowed researchers to study electricity in ways that had never been possible before. The invisible force was no longer only something found in nature. It had become something humans could create, something they could hold in their hands, something they could carry from one place to another. In the quiet laboratories of the early 19th century, scientists began connecting wires to batteries and watching the strange effects that followed. The relationship between electricity and magnetism was waiting to be discovered, and with the battery providing the first steady current, humanity was finally ready to uncover one of the greatest secrets of the natural world. Electricity was no longer just a spark. It was becoming a source of power. The invention of the battery changed everything. For the first time, scientists had a steady source of electrical current. Electricity was no longer only a momentary event. It was something that could flow. It could travel through wires. It could be measured. And with this new ability came a new wave of discoveries. Scientists began connecting batteries to different materials, observing what happened when electrical currents moved through the world around them. They soon discovered something remarkable. Electricity could create magnetism, and magnetism could influence electricity. The two mysterious forces that had fascinated humanity for centuries were connected. This discovery would eventually lead to electric motors, generators, power plants, and nearly every modern electrical technology. But the journey began with a simple observation made by a Danish scientist on a quiet day in 1820. His name was Hans Christian Ørsted. Ørsted was a professor of physics at the University of Copenhagen. He was deeply interested in the relationship between different forces in nature. Like many scientists of his time, he wondered whether electricity and magnetism might somehow be related. At first, this idea seemed unlikely. Magnets had been studied for centuries. Electricity, meanwhile, seemed like something completely different. One involved attraction between metals. The other involved sparks and currents. They appeared to belong to separate worlds. But Ørsted suspected there might be a hidden connection. During a demonstration with a battery and a wire, Ørsted noticed something unexpected. When electrical current flowed through the wire, a nearby compass needle moved. The electricity passing through the wire was creating a magnetic field. For the first time, humans had discovered that electricity could produce magnetism. The invisible forces of nature were connected. The discovery spread quickly throughout Europe. Scientists immediately began repeating Ørsted's experiment and exploring the possibilities. If electricity could create magnetism, perhaps magnetism could also create electricity. Among those fascinated by the discovery was the French mathematician and physicist André-Marie Ampère. Ampère began studying the relationship between electrical currents and magnetic forces. Through careful experiments, he discovered that electrical currents could influence one another. Two wires carrying electricity could attract or repel each other depending on the direction of the current. Ampère's work helped create the foundation of electrodynamics. His discoveries also helped scientists understand that magnetism was not a completely separate force. It was created by moving electrical charges. As scientists continued exploring electromagnetism, they began imagining new possibilities. If electricity could create magnetism, could it create motion? Could a wire carrying electricity somehow be made to move? Could electricity become a source of mechanical power? These questions would eventually lead to one of the most important inventions in human history, the electric motor. The early experiments began with simple devices. Scientists discovered that a wire carrying current placed near a magnet could experience movement. By carefully arranging magnets and electrical currents, they could create continuous rotation. The idea was revolutionary. For centuries, machines had been powered primarily by muscle, animals, wind, and steam. Now, a new form of power was emerging. Invisible energy could create motion. The connection between electricity and magnetism was becoming the bridge between science and industry. But perhaps the most important breakthrough of this era came from an English scientist named Michael Faraday. Faraday was born in 1791 into a poor family in London. Unlike many scientists of his time, he did not attend university as a young man. Instead, he began his career as an apprentice to a bookbinder. While working with books, he developed a fascination with science. He read everything he could find and attended public lectures whenever possible. Eventually, his curiosity led him to a position at the Royal Institution, where he worked alongside some of Britain's leading scientists. Faraday possessed a remarkable ability to imagine how invisible forces interacted. He was not known for complicated mathematics. Instead, he relied on careful experiments and powerful intuition. When he learned of Oersted's discovery, he became fascinated by the possibility of creating motion through electricity. In 1821, Faraday built one of the first devices that demonstrated electromagnetic rotation. A wire carrying electrical current moved continuously around a magnet. It was a small experiment, but it revealed a massive possibility. Electricity could create mechanical movement. The electric motor was beginning to take shape. Faraday continued studying electricity and magnetism for decades. His experiments explored how these forces interacted and how they could be transformed from one form into another. His most important discovery would come later with electromagnetic induction. Faraday discovered that changing magnetic fields could create electrical currents. This was the opposite of Oersted's discovery. Electricity created magnetism. Magnetism could create electricity. The relationship was complete. This discovery would become the foundation of the electrical generators that power the modern world. The same basic principle would eventually allow massive turbines in power plants to produce electricity for millions of homes. But in the early 19th century, these possibilities were still far away. Scientists were simply uncovering the hidden relationship between two invisible forces. They were learning that nature was not divided into separate pieces. Electricity and magnetism were part of the same story. The spark from a battery, the movement of a compass needle, and the pull of a magnet were all connected. The world was beginning to reveal a deeper pattern. The discovery of electromagnetism marked one of the great turning points in the history of electricity. The battery had provided a steady source of current. Now scientists understood how that current could interact with the world around it. Electricity was no longer just something to observe. It could create action. It could produce movement. It could become a tool. The age of electrical machines was approaching, and soon the invisible force that once existed only in lightning storms and tiny sparks would begin carrying messages, powering devices, and transforming civilization itself. In the early 19th century, Electricity was changing from a scientific curiosity into a force of possibility. The discoveries of batteries, electromagnetism, and electrical currents had opened a new world of questions. Scientists now knew that electricity could create magnetic effects, but they were still searching for ways to truly control this relationship. His name was Michael Faraday. Faraday's story was unusual. Unlike many famous scientists of his time, he was not born into wealth or privilege. Instead, his journey began in a modest neighborhood in London. Michael Faraday was born in 1791, the son of a blacksmith. His family struggled financially, and as a young boy, Faraday received only a basic education. At the age of 14, he became an apprentice to a bookbinder. But the bookbinding shop provided Faraday with something priceless: access to knowledge. While repairing books and preparing them for customers, Faraday discovered the writings of scientists and philosophers. He read about chemistry, physics, and the natural world with enormous curiosity. The pages passing through his hands became his education. He was especially fascinated by scientific experiments. He wanted to understand not just what happened, but why it happened. Faraday began attending public lectures at the Royal Institution in London, where some of Britain's leading scientists presented their discoveries. One of these scientists was the famous chemist Humphrey Davy. Faraday carefully recorded notes during Davy's lectures and later bound them into a book. He eventually sent the collection to Davy, hoping for an opportunity to work with him. His persistence paid off. In 1813, Faraday became a laboratory assistant at the Royal Institution. This position placed him in the center of scientific discovery. He worked alongside leading researchers, helped prepare experiments, and absorbed every piece of knowledge he could find. Over time, Faraday developed into an exceptional experimental scientist. He had a rare ability to imagine invisible forces at work. Where others saw isolated events, Faraday saw connections. When scientists discovered that electricity could move a compass needle, Faraday wondered whether the reverse might also be possible. Could magnetism create electricity? This question would occupy much of his life. During the 1820s, Faraday continued experimenting with electricity and magnetism. He studied how electrical currents created magnetic fields and explored ways to produce continuous motion. His early work led to the creation of one of the first electric motors. The device was simple compared to modern machines, but the idea behind it was revolutionary. A flow of electricity could create movement. An invisible force could produce mechanical action. For thousands of years, humans had relied on muscles, animals, wind, and water to power machines. Now, electricity had entered the world of motion. But Faraday was only beginning. His greatest discovery came in 1831 with his experiments on electromagnetic induction. Faraday discovered that moving a magnet near a coil of wire could create an electrical current. The important detail was movement. A stationary magnet did nothing. A moving magnet produced electricity. This discovery revealed a powerful new principle. Mechanical energy could be converted into electrical energy. The reverse of the electric motor had been discovered. Instead of using electricity to create motion, motion could now be used to create electricity. This was the foundation of the electrical generator. The importance of this discovery cannot be overstated. Nearly every modern power plant operates using Faraday's principle of electromagnetic induction. Whether the energy source is water, wind, coal, natural gas, or nuclear power, generators work by moving magnets through coils of wire to produce electricity. The lights in modern cities, the power running through homes, and the electricity that supports modern civilization all trace back to this simple discovery made in Faraday's laboratory. Yet despite the importance of his work, Faraday remained remarkably humble. He was more interested in discovery than fame. He spent countless hours in his laboratory, carefully recording observations and performing experiments. His notebooks were filled with drawings, measurements, and questions. Faraday believed that nature could reveal its secrets if scientists were patient enough to listen. His approach to science was different from many of his contemporaries. He was not primarily a mathematician. Instead, he relied on imagination, observation, and experimentation. He created demonstrations that allowed people to see invisible forces at work. Through iron filings, magnets, wires, and electrical currents, he made the hidden world of electromagnetism visible. Faraday also became known as a gifted teacher. Every year, he gave public lectures at the Royal Institution, including his famous Christmas lectures designed to introduce science to young audiences. He believed that science should not be locked away in laboratories. It should inspire curiosity in everyone. His demonstrations made complicated ideas feel understandable. A room full of people could watch magnets move, flames change color, and electrical effects appear before their eyes. Science became something people could experience. As Faraday's discoveries grew, so did his reputation. He was offered honors and recognition, but he remained focused on his work. He declined a knighthood and avoided positions that would distract him from research. For Faraday, the greatest reward was understanding nature. His discoveries transformed the way humanity viewed electricity. Before Faraday, electricity was something scientists studied. After Faraday, electricity became something engineers could use. His work provided the bridge between scientific discovery and practical technology. The electric motor and generator would eventually become essential parts of modern life. Machines would operate with the invisible force Faraday helped reveal. But in the quiet rooms of the Royal Institution, the significance of these discoveries was still unfolding. A humble scientist who began his career as a bookbinder's apprentice had uncovered one of nature's deepest connections. Electricity and magnetism were not separate mysteries. They were two parts of the same invisible world. And with Faraday's discoveries, humanity had taken another enormous step toward the electrical age. The spark had become a current. The current had become a force. For most of human history, distance was one of the greatest obstacles people faced. The world was large, and information moved slowly. But in the 19th century, a remarkable idea began to emerge. What if messages could travel faster than people? The answer came through one of humanity's earliest practical uses of electricity: the telegraph. The telegraph was a revolutionary invention because it transformed electricity from a force studied in laboratories into a tool that connected the world. For the first time, humans learned how to use electrical currents to send information across wires. The idea of using electricity for communication had existed for many years before the telegraph became practical. Early scientists experimented with electrical signals traveling through wires. They imagined systems where different electrical pulses could represent letters or numbers. However, these early ideas faced major challenges. Electricity was still difficult to control, and scientists had not yet developed a simple system for turning electrical signals into meaningful messages. The breakthrough came when inventors began combining electrical science with a simple communication system. One of the most important figures in the development of the telegraph was Samuel Morse. Born in Massachusetts in 1791, Morse was not originally an electrical scientist. He was an artist. Morse studied painting and became a respected portrait artist. For much of his early life, his focus was on creating works of art rather than inventing machines. But during a trip across Europe in the 1830s, Morse became fascinated by new discoveries in electricity. He learned about electromagnetism and began wondering whether electrical signals could be used to send messages over long distances. The idea was simple but powerful. A person could press a key, creating a pattern of electrical pulses. Those pulses could travel through a wire. At the other end, a machine could record the signals. The challenge was creating a system that could translate those pulses into understandable information. Morse worked with other inventors and eventually developed a code that would become famous throughout the world. Morse code. Instead of sending entire letters, the system used combinations of short and long signals called dots and dashes. Each letter of the alphabet had its own pattern. Operators trained themselves to recognize these patterns and translate them into words. The system was simple, efficient, and surprisingly effective. The first successful long-distance telegraph demonstrations proved that electricity could carry messages faster than any human messenger. In 1844, Samuel Morse sent one of the most famous messages in communication history from Washington, D.C., to Baltimore. The message traveled through a wire stretched between the two cities. A signal created in one location appeared almost instantly in another. Before the telegraph, news traveled at the speed of transportation. After the telegraph, news traveled at the speed of electricity. This transformed businesses, governments, newspapers, and everyday life. Companies could coordinate activities across great distances. Financial markets received information more quickly. The world began to feel connected in a new way. Telegraph offices appeared in cities and towns across continents. Inside these buildings, operators sat quietly at their instruments, listening to the rhythmic tapping of electrical messages. A message arrived not as a voice or a written letter, but as a pattern of sounds and movements. A trained operator could hear the difference between short and long signals and transform the electrical language into words. As telegraph networks expanded, engineers began building thousands of miles of wire across landscapes. Poles stretched along roads and through fields. Lines crossed mountains, deserts, and forests. The physical world became covered with pathways for invisible messages. One of the greatest achievements of the telegraph era was the connection between continents. For centuries, oceans had separated people and nations. Ships carried letters and information across the water, often requiring weeks to arrive. But in the 1800s, engineers began working on underwater telegraph cables. These massive projects were incredibly difficult. The ocean floor was deep and unpredictable. Cables could break under pressure or fail after being installed. But eventually, success came. In 1858, the first transatlantic telegraph cable was completed, connecting North America and Europe. Although the cable only worked briefly before failing, it proved that global communication through electricity was possible. Later improvements created reliable connections that permanently changed international communication. Messages that once required weeks could now travel across the Atlantic in minutes. The world had entered a new age. Electricity was no longer simply a scientific phenomenon. It had become a force that could overcome distance itself. The telegraph also changed the way people thought about time. Before electricity, people lived according to local rhythms. A town's clocks were set according to the position of the sun. Communities operated independently, separated by geography. But as telegraph networks expanded, coordination became increasingly important. Railroads needed precise schedules. Businesses needed accurate timing. Information needed to move quickly. The electrical age was beginning to create a more connected world. Although the telegraph may seem simple compared to today's technology, it represented a profound transformation. It was the first major invention to use electricity not to create heat, light, or movement, but to transmit information. It proved that electricity could carry human thoughts from one place to another. The same invisible force that once appeared only as a spark in a laboratory could now cross entire countries. A message created by human hands could become an electrical signal, travel through wires, and emerge as words thousands of miles away. The telegraph was humanity's first step toward the connected world we know today. It paved the way for telephones, radio, television, computers, and the Internet. But before voices could travel through wires, and before digital messages could cross the globe in seconds, there was the quiet tapping of the telegraph key, a simple rhythm of dots and dashes, a language carried by electricity. The invisible force had found its voice. For thousands of years, humanity had depended on fire to push back the darkness. Light had always required something to burn. The flame was beautiful, but it was also limited. Candles needed to be replaced. Oil lamps produced smoke and required fuel. Fires needed constant attention. As cities grew larger during the 19th century, the need for better lighting became increasingly important. The industrial world was expanding. Factories operated late into the evening. Businesses wanted longer working hours. Cities wanted safer streets. People dreamed of a future where darkness could be defeated without relying on thousands of individual flames. Electricity seemed like the answer. But creating practical electric light was one of the greatest challenges of the early electrical age. Scientists had already discovered how to create electricity. They had learned how to send electrical signals across wires. They had even discovered how electricity and magnetism were connected. But transforming electricity into a reliable source of light was much more difficult. The journey toward the electric light would involve decades of experiments, countless failures, and many inventors searching for the right combination of materials. The first major attempts at electric lighting began with a device called the arc lamp. Unlike the incandescent bulbs that would later become common in homes, arc lamps created light by producing a powerful electrical spark between two carbon rods. When electricity passed between the rods, it created an incredibly bright arc of light. The effect was impressive. For the first time, electricity could create a light source brighter than candles or oil lamps. However, early arc lamps had serious problems. They were extremely bright, making them unsuitable for homes. They produced intense heat. They required constant adjustment as the carbon rods slowly burned away. And they were expensive. Still, arc lamps proved something important. Electricity could create artificial light. The dream was possible. Scientists now needed to find a better way. The ideal electric light would need to be smaller, safer, and more practical. It needed to be something that ordinary people could use in their homes. The challenge was finding a material that could glow when electricity passed through it without quickly burning away. This problem fascinated inventors around the world. Throughout the 19th century, researchers experimented with many different materials. They tried platinum wires. They tested carbon. They used various metals and fibers. Some experiments worked briefly. A material might glow for a few seconds before breaking apart. Others lasted a little longer, but were too expensive or unreliable. Each failure provided another clue. The problem was not whether electricity could create light. It clearly could. The problem was controlling it. Scientists needed a way to make a tiny piece of material become hot enough to glow while lasting long enough to be useful. This process required understanding resistance, heat, and electrical currents. The work of scientists studying electromagnetism and electrical engineering made these discoveries possible. As knowledge grew, inventors moved closer to creating a practical lamp. One important early contributor was British inventor Joseph Swan. Swan began experimenting with incandescent lighting in the 1850s and 1860s. He developed a lamp that used a carbon filament inside a glass bulb. The idea was simple. If the filament was placed inside a vacuum, removing most of the oxygen, it would not burn away as quickly. The filament could become hot enough to glow. Swan's experiments were successful, but creating a truly practical bulb remained difficult. The filament had to be durable. The vacuum had to be reliable. The electrical system powering the bulb had to be efficient. The invention of electric lighting was not just about creating a bulb. It required creating an entire system. Electricity needed to be generated. It needed to be distributed. Buildings needed wiring. People needed a reason to adopt the technology. The electric light was part of a much larger transformation. This was the challenge that would later be taken on by Thomas Edison and other inventors. But before the famous light bulb became a symbol of invention, many lesser-known scientists and engineers had already laid the groundwork. The progress toward electric lighting was a shared effort. Each experiment added another piece to the puzzle. During this period, cities were also changing. Gas lighting had become increasingly common during the 19th century. Streets were illuminated by gas lamps, and workers known as lamplighters walked through neighborhoods each evening, lighting the flames one by one. It was a familiar sight. As twilight arrived, a lamplighter would carry a long pole through the streets, opening valves and bringing the city to life. The introduction of electric lighting promised something different. No individual needed to light each lamp. No gas lines were required throughout buildings. A simple switch could eventually provide instant illumination. The idea was revolutionary. Imagine living in a world where every evening required preparing lamps, trimming wicks, and carrying matches. Then imagine a future where a room could suddenly glow with the movement of a finger. Electric light represented more than convenience. It represented control over time itself. For the first time, humans could create daylight whenever they wanted. The boundary between day and night began to change. Factories could operate longer. People could read and work after sunset. Cities became places that never fully slept. The night was no longer simply a time of darkness. It became another part of the day. By the late 19th century, the race to create a practical electric light was accelerating. Inventors across the world were searching for the perfect design. They experimented with materials, improved electrical systems, and studied the behavior of currents. The breakthrough was approaching. Soon, electric lights would move from laboratories and demonstrations into homes and businesses. The glow of a new age was about to begin. But the electric light would require more than a brilliant invention. It would require an entire electrical network capable of bringing power to millions of people. The future would not simply be a world with light bulbs. It would be a world connected by electricity. And that transformation would begin in the workshop of one of history's most famous inventors. By the late 19th century, the dream of electric light was closer than ever. Scientists had learned that electricity could create illumination. Inventors had created early lamps that glowed brightly for short periods of time. Engineers understood many of the principles needed to build electrical systems. But one major challenge remained. Electric lighting needed to become practical. A lamp that worked for a few minutes in a laboratory was not enough. The world needed a light that could be used every day. Creating the electric light was not just about inventing a bulb. It was about creating an entire electrical world. The person who became most closely associated with this transformation was Thomas Edison. Born in 1847 in Milan, Ohio, Edison grew up with an intense curiosity about the world around him. From an early age, he was fascinated by experiments, machines, and the way things worked. Unlike many inventors of his era, Edison did not spend most of his time working alone. He built something new, a research laboratory designed specifically for invention. At Menlo Park, New Jersey, Edison gathered skilled assistants, engineers, and experimenters who worked together to solve difficult problems. The laboratory became a place where ideas could be tested, improved, and transformed into practical inventions. Edison's approach was methodical. He believed invention was not simply a moment of inspiration. It was a process. A problem was identified. Experiments were performed. Failures were recorded. New approaches were tested. Then the process began again. This patience was especially important in his search for a practical incandescent light bulb. The challenge was enormous. The filament inside the bulb needed to become hot enough to glow, but it could not burn away too quickly. The glass bulb needed to contain a vacuum to protect the filament. The electrical current had to be carefully controlled. Every small detail mattered. Edison and his team tested thousands of different materials. They experimented with metals, plant fibers, carbonized materials, and countless other possibilities. Many failed almost immediately. Some filaments glowed brightly, but lasted only seconds. Others survived longer, but produced too little light. Each attempt brought new information. Slowly, the right combination began to appear. In 1879, Edison and his team successfully created a practical incandescent lamp using a carbonized bamboo filament. The bulb burned for many hours, proving that electric lighting could become a reality. The achievement was remarkable, but Edison understood that the bulb itself was only one piece of the puzzle. A light bulb without a source of electricity was useless. To bring electric lighting into homes and businesses, Edison needed to build an entire system. This meant creating generators powerful enough to produce electricity. It meant designing underground wiring networks. It meant developing switches, meters, and safety systems. It meant convincing people that electricity was not just a scientific curiosity, but a useful part of everyday life. Edison's vision was ambitious. He imagined cities where electricity flowed quietly beneath streets, providing power whenever people needed it. The first major demonstration of this vision came in New York City. In 1882, Edison opened the Pearl Street Station, one of the world's first central power stations. The station generated electricity and distributed it to nearby customers through a network of underground wires. On September 4, 1882, parts of Lower Manhattan were illuminated by electric light. For many people, it was their first experience with this new technology. The change must have felt almost impossible. For centuries, nighttime meant darkness interrupted only by small flames. Now, entire streets could glow. Buildings could remain active after sunset. A new relationship with time was beginning. Electricity was extending the day. The arrival of electric lighting also transformed cities. Gas lamps had required workers to manually light and maintain them each evening. Electric lights could be switched on instantly. Businesses could operate longer. Factories could work beyond daylight hours. Public spaces became brighter and safer. The nighttime city was being reinvented. However, Edison's success did not mean the electrical age arrived overnight. Early electrical systems were expensive and limited. Power stations could only serve relatively small areas. Homes needed to be connected to electrical networks. People needed to purchase electrical devices. The infrastructure had to grow. But the foundation had been built. Electricity had moved from the laboratory into the streets. It had become part of daily life. The impact was not only practical. Electric light also changed how people experienced their homes. Before electricity, evening activities were organized around lamps and candles. Reading required sitting close to a light source. Families gathered around specific areas of illumination. Rooms were designed around the placement of lamps and fireplaces. Electric lights changed that. A room could be illuminated evenly. People could work, read, and socialize more easily. The home itself began adapting to electricity. The electric age was becoming a cultural change as much as a technological one. Yet Edison's electrical system was not the only approach being developed. A major debate was beginning among electrical engineers. What kind of electricity should power the future? Edison's system used direct current, or DC. It worked well for nearby buildings but had limitations. Electricity could not easily travel long distances using this method. Another approach was beginning to emerge. Alternating current, or AC, offered the possibility of transmitting electricity over much greater distances. This difference would eventually lead to one of the most famous rivalries in technological history. The battle over the future of electricity was just beginning. But before that competition unfolded, Edison's achievements had already changed the world. He helped transform electricity from a scientific experiment into a practical technology. He showed that invisible energy could be generated, distributed, and used to improve everyday life. The flickering flame had been replaced by the steady glow of the electric lamp. The darkness that had surrounded humanity for thousands of years was slowly retreating. The electric age had arrived, and the world was about to discover just how powerful this invisible force could become. By the end of the 19th century, electricity had begun transforming the world. Cities were glowing with electric lights. Businesses were adopting new electrical machines. Homes were slowly becoming connected to power networks. The dream of an electrified society was no longer just an idea. It was becoming reality. But as electricity spread, a major question remained. What kind of electricity would power the future? There were two competing visions. One used direct current, or DC. The other used alternating current, or AC. The disagreement over these systems became one of the most famous conflicts in the history of technology. It became known as the War of the Currents. At the center of this struggle were two very different inventors, Thomas Edison and Nikola Tesla. Both men changed the course of electrical history. Both believed they were building the future, but they imagined that future in very different ways. Thomas Edison's electrical system relied on direct current. In a direct current system, electricity flows continuously in one direction from the power source to the device using it. Edison's early power stations generated DC electricity and distributed it to nearby customers. The system worked. It powered lights. It proved that electricity could be delivered to homes and businesses. But it had a major limitation. Direct current did not travel efficiently over long distances. As electricity moved through wires, energy was lost as heat. To provide power to distant locations, many additional power stations would be needed. This meant that Edison's system worked best in dense urban areas where customers were close to a generating station. But the world Edison imagined would require something much larger. Electricity needed to travel beyond a few city blocks. It needed to cross neighborhoods, towns, and eventually entire regions. A different approach was needed. That approach came from alternating current. Unlike direct current, alternating current periodically changes direction. This may seem like a small difference, but it created a major advantage. Using transformers, AC electricity could be increased to very high voltages for long-distance transmission and then reduced to safer levels for homes and businesses. Electricity could travel much farther with less energy loss. The person who helped reveal the incredible potential of alternating current was Nikola Tesla. Tesla arrived in the United States in 1884 with little money but great ambition. He briefly worked for Edison's company, helping improve electrical equipment. However, their relationship did not last. Tesla believed that alternating current was the better solution for the future of electrical power. Edison disagreed. The two inventors had different ideas about how electricity should develop. Tesla eventually began working with industrialist George Westinghouse, who recognized the potential of Tesla's AC system. Westinghouse believed that alternating current could provide electricity to a much larger area. Together, Tesla and Westinghouse began developing AC technology. The competition between the two systems became intense. Edison strongly defended direct current. He argued that AC electricity was dangerous because of the high voltages used in transmission. Tesla and Westinghouse continued improving their system. They developed better transformers, generators, and motors that made alternating current practical. Tesla's inventions were especially important. He developed the induction motor, which used alternating current to create a rotating magnetic field. This invention allowed electricity to power machines without requiring complicated mechanical systems. The electric motor became one of the foundations of modern industry. The debate between AC and DC reached a dramatic moment during the 1890s when both systems competed for major projects. One of the most important was the creation of a large hydroelectric power station at Niagara Falls. The project aimed to harness the power of falling water and convert it into electricity. The question was, which electrical system would be used? The answer would shape the future. In 1895, the Niagara Falls Power Project chose alternating current. The success of the project demonstrated that AC could power large regions efficiently. The war of the currents was effectively decided. Alternating current became the dominant method for electrical distribution around the world. But the story of Edison, Tesla, and Westinghouse is not simply one of victory and defeat. Each contributed enormously to the electrical age. Together, their work created the foundation of the modern electrical grid. The impact of this transformation was enormous. Electricity was no longer limited to small areas around individual power stations. It could be generated in one location and transported across great distances. This made possible the electrification of entire cities and eventually entire countries. The world began changing at an incredible pace. Factories replaced steam-powered machines with electric motors. Streetcars powered by electricity began carrying passengers through cities. Buildings gained elevators, allowing them to grow taller. Homes slowly began adopting electric appliances. The invisible force discovered through tiny sparks and laboratory experiments had become the engine of modern civilization. Yet despite the enormous importance of his work, Nikola Tesla's later years were filled with financial struggles and unfinished ideas. He imagined a future of wireless communication and limitless electrical possibilities, but many of his dreams remained unrealized during his lifetime. Edison continued inventing and building companies, becoming one of the most famous figures of the age. Their rivalry became legendary because it represented more than a disagreement between two inventors. It represented a fundamental question about the future. How would humanity use electricity? The answer was eventually found not in one invention or one person, but through the combined efforts of countless scientists, engineers, and innovators. Electricity was too powerful to belong to a single vision. It would become a force that connected the entire world. The War of the Currents marked the moment when electricity moved beyond individual buildings and became a true global system. The age of electric power had begun, and the quiet current flowing through wires would soon reshape nearly every part of human life. A new challenge emerged. How could electricity become part of everyday life? A power station could illuminate a city street, but what about the homes of ordinary families? How could this invisible force move from distant generating plants into kitchens, bedrooms, workshops, and living rooms? The answer required the creation of an entirely new world of electrical infrastructure. The electrical age was not built with a single invention. It was built with miles of wires, new machines, new businesses, and a gradual change in the way people lived. At first, electricity was considered a luxury. When electric lighting first appeared in the late 19th century, it was mostly found in wealthy homes, businesses, theaters, and public buildings. For many people, electricity was something they saw rather than something they used. A person might walk through a city and admire glowing storefronts or bright streetlights, but their own home might still rely on candles, oil lamps, and gas lighting. The transition was slow. Electricity required trust. People had to believe it was safe. They had to understand how to use it, and they had to be willing to pay for a technology that was unfamiliar. Early electrical systems were expensive, and many families saw little reason to replace familiar sources of light. A candle was simple. A gas lamp was understood. Electricity was mysterious. But as electrical networks expanded, the advantages became impossible to ignore. Electric lights were cleaner. They did not produce smoke like candles or gas lamps. They could be turned on instantly. They required less maintenance, and they allowed people to control their environment in ways that had never been possible before. A simple switch could bring light into a dark room. This small action represented a remarkable change in human history. For thousands of years, people had adapted their lives around available light. They woke with the sun. They worked during daylight. They gathered near sources of flame after dark. Now, light could appear whenever people wanted it. Nighttime was beginning to change. The home itself began transforming around electricity. Electrical wiring became a new feature of buildings. Instead of carrying fuel to lamps, families could rely on power flowing invisibly through walls. Homes gained electrical outlets. Switches appeared on walls. Rooms could be illuminated without carrying matches, trimming wicks, or maintaining flames. At first, many electrical devices were simple. Electric bells allowed people to signal across buildings. Small motors powered fans and other machines. Electric irons replaced some of the work previously done with heated metal. These early appliances introduced families to a new idea. Electricity was not just for lighting. It could perform work. It could save time. It could make daily tasks easier. The growth of household electricity also changed the role of women and domestic work. Many household tasks required significant time and physical effort. Laundry, cooking, cleaning, and food preparation were labor-intensive activities. Electrical appliances promised to reduce some of this burden. The washing machine, vacuum cleaner, refrigerator, and electric stove would eventually become common household tools, transforming everyday routines. However, these inventions did not appear all at once. The electrical home developed gradually. Manufacturers had to create reliable devices. Electric companies had to expand their networks. Consumers had to become comfortable with new technology. The spread of electricity was a partnership between invention and adoption. One of the biggest challenges was making electricity available beyond large cities. Early power stations were concentrated in urban areas where many customers could be served in a small space. Rural communities often remained without electricity for decades. A city might glow with electric lights while a nearby farm continued relying on lanterns and fireplaces. Bringing electricity to rural areas required enormous investment. Power lines needed to cross long distances. Weather conditions had to be considered. Infrastructure had to be built across farms, forests, and mountains. Eventually, governments and utility companies began expanding electrical networks more widely. The goal was not just convenience. Electricity became a symbol of progress and modernization. Communities saw electrical connections as a sign that they were joining the future. The arrival of electricity often became a major local event. A new power line reaching a town could change daily life almost immediately. Farmers could use electric pumps. Businesses could operate longer. Schools could use new equipment. Families could enjoy brighter, safer homes. The electrical grid slowly became one of the most important systems in society. But electricity did more than change homes. It changed the way people thought about time and productivity. Before electricity, many activities were limited by daylight. Factories needed large windows to capture sunlight. Workers often stopped when darkness arrived. Businesses closed earlier. Electric lighting extended the usable hours of the day. A factory could continue operating after sunset. A student could read late into the evening. A family could gather after dinner without relying on a dim flame. The boundary between day and night became flexible. Electricity gave humanity control over something that had shaped life for thousands of years: time. The spread of electricity also changed entertainment. Theaters adopted electric lighting to create dramatic effects. Cities developed illuminated streets and signs. Amusement parks used electric displays to attract visitors. The nighttime landscape became brighter and more exciting. People began experiencing cities in a completely new way. The electric age was not only practical, it was beautiful. The glow of electric lights became a symbol of modern life. By the early 20th century, electricity had moved from laboratories and wealthy neighborhoods into the foundations of everyday society. It powered homes. It illuminated streets. It supported businesses. It connected communities. The invisible force that once appeared only as lightning in the sky had become a constant companion in human life. Yet the electrical revolution was still just beginning. Electricity had entered homes, but soon it would begin transforming communication, entertainment, transportation, and industry in ways that few people could imagine. The world had learned how to create electricity. Now it was learning what electricity could do. For centuries, factories had depended on mechanical power sources. Water wheels turned machines along rivers. Steam engines powered equipment in industrial cities. Workers operated machines by hand. These systems had transformed the world, but they had limitations. Steam engines were large. They required constant fuel. They needed extensive mechanical systems to transfer power throughout a factory. Electricity offered something entirely different. It was flexible. It could be delivered almost anywhere. It could power small machines or enormous industrial systems. It could be controlled with the movement of a switch. The factory of the future would not be built around a single massive engine. It would be built around electricity. The arrival of electric motors changed manufacturing forever. Before electric motors became common, many factories relied on a central steam engine connected to a complicated network of belts, shafts, and gears. The engine created power in one location, and mechanical systems transferred that power throughout the building. This arrangement was inefficient. Machines had to be positioned near the power source. Factory layouts were limited by the need for mechanical connections. Electric motors changed this system completely. Instead of one enormous engine powering an entire factory, individual machines could have their own motors. A machine could be placed wherever it was needed. Factories could be designed more efficiently. Electricity gave manufacturers freedom. One of the most important industries transformed by electricity was manufacturing. Factories began using electric motors to power drills, lathes, presses, and assembly equipment. Production increased. Costs decreased. The modern industrial world began taking shape. Electricity also changed the way factories operated. With improved lighting, workers could safely continue production after sunset. Factories no longer depended entirely on daylight. The working day became longer, and industrial output increased. This transformation helped accelerate economic growth around the world. One of the most famous examples of electricity transforming industry was the automobile factory. In the early 20th century, the automobile industry was developing rapidly. Electric-powered machinery helped make mass production possible. The introduction of assembly line manufacturing, especially at the Ford Motor Company, demonstrated how electricity could support a new style of production. Instead of skilled workers building an entire product from beginning to end, each worker could specialize in a specific task. Parts moved through the factory using carefully organized systems. Electric motors powered the equipment that made this process possible. The result was a dramatic increase in production. Products that were once expensive and rare became available to more people. Electricity was not simply powering machines. It was changing the relationship between humans and manufacturing. Beyond factories, electricity also transformed transportation. One of the earliest uses of electric power in cities was the electric streetcar. Before electric streetcars, urban transportation depended heavily on horses. Horse-drawn vehicles were slow, expensive to maintain, and created major sanitation problems. Electric streetcars provided a cleaner and more efficient alternative. Tracks were installed throughout cities, and electric motors powered vehicles that carried passengers through neighborhoods. Cities expanded outward as transportation improved. People could live farther from their workplaces and still travel efficiently. Electric transportation helped shape the modern city. Subways also began adopting electric power. Underground transportation had previously been limited by the problems of steam engines producing smoke and heat in enclosed spaces. Electric motors solved these problems. Cities like London and New York developed underground rail systems that relied on electricity. The result was a new era of urban movement. Electricity also transformed communication. The telegraph had already demonstrated that electrical signals could carry messages. But new technologies were beginning to emerge. The telephone, developed in the late 19th century, allowed voices to travel through electrical signals. For the first time, people could communicate instantly by speaking rather than sending coded messages. The telephone changed business, personal relationships, and daily life. A person no longer needed to wait for a letter or travel across town to have a conversation. A voice could travel through wires. The world was becoming smaller. Electricity was creating connections. The entertainment world also entered the electrical age. The development of electric recording, motion pictures, and broadcasting technologies opened new forms of communication and recreation. Movie theaters used electric lighting and projection systems. Radio technology allowed voices and music to travel through the air. Families could gather around electrical devices and experience entertainment together. Electricity was becoming part of culture itself. However, the rapid growth of electrical technology also created new challenges. Cities needed more power. Industries demanded larger electrical systems. Engineers had to develop safer and more reliable methods of generating and distributing electricity. Power plants grew larger. Transmission lines stretched farther. The electrical grid became one of the most complex systems ever created by humans. By the middle of the 20th century, electricity had become essential to modern life. It powered factories that produced goods. It moved people through cities. It connected communities. It supported communication. It changed entertainment. The invisible force discovered through simple experiments had become the foundation of an industrial civilization. But perhaps the most remarkable part of electricity's transformation was how quickly it happened. Only a few generations earlier, people lived in a world lit by candles and powered by animals. Now, cities were filled with electric machines operating day and night. The difference between the past and the present was enormous. Electricity had become the quiet force behind progress. It was hidden inside walls, buried beneath streets, carried through wires stretching across landscapes. Most people rarely thought about it. They simply flipped a switch and expected the world to respond. But behind that simple action was centuries of discovery, experimentation, and invention. The age of electricity had fully arrived. The telegraph had shown that electrical signals could travel through cables. The telephone had allowed voices to move through electrical connections. But what if communication did not require wires at all? What if electricity could travel invisibly through the air? This idea seemed impossible to many people. Yet hidden within the discoveries of electricity and magnetism was a possibility that would eventually connect the entire world. The age of wireless communication was about to begin. The foundation for this revolution came from the work of Scottish physicist James Clerk Maxwell. In the 19th century, scientists had already discovered that electricity and magnetism were connected. Ørsted had shown that electricity could create magnetic effects. Faraday had demonstrated that magnetism could produce electricity. Maxwell took these discoveries further. Through careful mathematical work, he developed a theory explaining that electricity and magnetism were not separate forces, but parts of the same phenomenon. He predicted the existence of electromagnetic waves. These waves could travel through space, carrying energy from one location to another. Maxwell's ideas were revolutionary. They suggested that invisible waves could move through the world around us, even through empty space. At the time, this was only a theory. No one had yet proven that these waves existed. That changed with the experiments of German physicist Heinrich Hertz. In the late 1880s, Hertz created equipment that could produce and detect electromagnetic waves in a laboratory. His experiments confirmed Maxwell's predictions. The invisible waves were real. Electricity and magnetism could travel through space. Humanity had discovered a new way to interact with the world. Although Hertz was primarily interested in proving a scientific theory, his work inspired inventors to consider practical applications. If electromagnetic waves could travel through the air, perhaps they could carry messages. The possibility of wireless communication began to emerge. One of the people who recognized this potential was Guglielmo Marconi. Born in Italy in 1874, Marconi became fascinated with the idea of using radio waves to send signals over long distances. While still a young man, he began experimenting with wireless transmitters and receivers. His early equipment was simple. A device created electrical oscillations. An antenna sent those signals into the air. A receiver detected them at another location. At first, the distances were short. But Marconi continued improving his designs. Each experiment pushed the signal farther. Across gardens, across fields, across increasingly greater distances. By the late 1890s, Marconi had demonstrated wireless communication over several miles. The idea that messages could travel without wires was no longer a dream. It was becoming reality. The technology quickly attracted attention from governments, businesses, and especially the maritime industry. Ships had always faced a major communication challenge. Once a vessel left the harbor, it was isolated from the world. If something went wrong, there was little way to call for help. Radio changed that. Ships could now send messages while far from shore. They could communicate with other vessels. They could receive weather information. They could request assistance during emergencies. The ocean was no longer a complete barrier. One of the most famous demonstrations of radio's importance came during the sinking of the RMS Titanic in 1912. The ship carried wireless communication equipment that allowed operators to send distress signals after the collision with an iceberg. The emergency messages helped bring rescue efforts and demonstrated the life-saving potential of radio technology. Wireless communication had proven its value. But radio was not only useful for emergencies. It also changed entertainment and culture. In the early 20th century, inventors discovered that radio waves could carry not only simple signals, but sound, voices, music, news. For the first time, people could gather in their homes and listen to events happening far away. The radio became one of the most influential technologies of the 20th century. Families gathered around wooden radio sets in their living rooms. They listened to music, sports broadcasts, dramatic programs, and news reports. A voice traveling through invisible waves could enter millions of homes at once. The world was becoming connected in a completely new way. Radio changed politics, entertainment, and communication. A leader could speak directly to citizens across an entire country. Musicians could reach audiences far beyond their local communities. News could spread almost instantly. Electricity had become a bridge between people. The development of radio also encouraged new discoveries in electronics. Scientists began creating more advanced components that could control electrical signals. Vacuum tubes became important tools for amplifying and processing electrical information. These devices allowed radio receivers to become more sensitive and powerful. They also became important foundations for early computers and electronic technology. The invisible world of electricity was becoming more sophisticated. But the expansion of electrical communication also changed how humans understood distance. For most of history, distance meant separation. A mountain range, ocean, or great stretch of land could isolate communities. Electric communication began breaking down those barriers. A message could cross a continent. A voice could travel across oceans. Information could move faster than people. The world was becoming smaller. By the early decades of the 20th century, electricity had transformed from a natural mystery into a global network. It powered machines. It illuminated cities. It carried messages through wires. And now it could send information through the air. The same force that once appeared only as lightning during storms had become a foundation for human connection. Yet scientists were still discovering new possibilities. Electricity had entered homes and industries, but the next generation of inventors would use it to create entirely new forms of technology. The coming decades would bring television, computers, digital devices, and a world where electricity would become nearly invisible because it was everywhere. The age of electrical connection had begun, and the invisible waves moving quietly through the air were only the beginning. By the middle of the 20th century, electricity had become something most people could no longer imagine living without. But perhaps the greatest transformation happened quietly inside ordinary homes. The modern household was being redesigned around electricity. The kitchen, the living room, the laundry room, and even the way families spent their evenings were changing. For centuries, household work depended heavily on physical labor. Many everyday tasks were time-consuming and exhausting. Electric appliances promised something revolutionary. They promised to save time. They promised convenience. They promised a home where machines could perform some of the hardest work. The arrival of household electricity was gradual. Electricity itself was still a new concept, and some people questioned whether these machines were truly necessary. But as manufacturing improved and prices decreased, electrical appliances slowly became more common. One of the earliest and most important household inventions was the electric refrigerator. Before refrigerators became widespread, families had to preserve food using iceboxes. An icebox was a simple insulated container where large blocks of ice kept food cool. The system worked, but it required regular deliveries of ice and careful management. Electric refrigeration changed everything. A machine could now create cold temperatures continuously. Families could store food longer. The refrigerator quietly transformed eating habits and food distribution. It affected not only homes but entire industries. Farmers, grocery stores, and transportation systems adapted to a world where food could be preserved and moved more easily. Another major household transformation came through the washing machine. For generations, laundry had been one of the most physically demanding household tasks. Electric washing machines changed this. A motor could move clothing through water and reduce much of the manual work. The machine became a symbol of how electricity could reduce everyday labor. The vacuum cleaner brought a similar change. Before electric vacuum cleaners, cleaning floors and carpets required sweeping and beating dust out of fabrics. Electric-powered suction created a new way of maintaining homes. The vacuum cleaner represented a broader trend. Electricity was replacing repetitive physical tasks with mechanical assistance. The home was becoming a place where machines quietly worked in the background. The kitchen became one of the greatest examples of this transformation. Electric stoves replaced many traditional cooking methods. Toasters made breakfast faster. Mixers and other small appliances changed food preparation. The kitchen became a space filled with specialized electrical tools designed to save time and effort. The introduction of these appliances also changed the way people thought about comfort. Electric fans provided relief during hot weather. Electric heaters helped warm homes. Water heaters provided hot water on demand. Small conveniences that once required planning and effort became available instantly. A person could flip a switch and receive immediate results. This expectation would become one of the defining characteristics of modern life. Electricity also transformed entertainment inside the home. The radio had already brought voices and music into living rooms. But new technologies soon followed. Television became one of the most influential electrical inventions of the 20th century. Early televisions were experimental and expensive, but by the middle of the century they became common household devices. Families gathered together to watch programs, news, and live events. The living room became a place where people could experience events happening far away. A person sitting at home could watch a speech, a sporting event, or a performance occurring hundreds or thousands of miles away. Electricity had changed not only how people worked, it changed how they experienced the world. The spread of household appliances also influenced architecture and home design. Homes began including more electrical outlets. Kitchens were redesigned around appliances. Rooms were arranged around lighting and entertainment systems. The electrical home became a new kind of environment. The relationship between people and their homes was changing. A house was no longer just a shelter. It was becoming a connected system of machines and devices. However, the benefits of household electricity were not distributed equally at first. Urban areas often received electrical service before rural communities. Wealthier families were able to purchase appliances earlier than others. For many households, electrification was a gradual process that occurred over decades. Programs to expand rural electricity became especially important in the 20th century. Bringing electricity to farms and remote communities transformed agricultural life. Electric pumps provided water. Electric lighting improved safety. Machines reduced physical labor. Rural electrification became a symbol of progress and opportunity. The arrival of electricity often changed communities permanently. Schools could use new equipment. Businesses could operate more efficiently. Families gained access to technologies once available only in cities. By the middle of the 20th century, electricity had become deeply woven into human life. Most people no longer thought about where it came from. They simply expected it to be available. A switch would create light. A refrigerator would preserve food. A radio would provide music. A television would bring the world into the home. Electricity had become invisible because it had become ordinary. Yet behind every ordinary convenience was a remarkable history of discovery. The sparks studied by early scientists. The batteries built in quiet laboratories. The experiments of Faraday and Tesla. The power stations built by Edison and Westinghouse. All of these discoveries had led to a world where electricity surrounded people every day. The electrical age had entered its most personal chapter. It was no longer only about cities, factories, and communication networks. It was about the small moments of daily life. The morning coffee made with an electric appliance. The evening spent listening to music. The simple act of turning on a light. Electricity had become part of the rhythm of human existence. And as the 20th century continued, a new revolution was approaching. Electricity would no longer just power machines. It would begin powering information itself. The age of computers was about to begin. For centuries, humans had created tools to help with calculation. Ancient civilizations used counting boards and mechanical devices to organize numbers. Later inventors built increasingly complex machines designed to perform mathematical tasks. But these machines were limited. electricity offered a new possibility. A machine could process information using electrical signals. Instead of moving mechanical parts, information could be represented by patterns of electrical activity. The idea was revolutionary. The same force that carried messages through telegraph wires could potentially carry instructions and calculations. The first steps toward electronic computing came during the early 20th century, as scientists developed new electrical components. One of the most important inventions was the vacuum tube. Originally developed for radio technology, vacuum tubes allowed engineers to control the movement of electrical signals. A switch that could be controlled electronically was the basic building block of early computers. During World War II, the demand for faster calculations accelerated computer development. Governments and scientists needed machines capable of solving complex mathematical problems. Calculating artillery trajectories, analyzing codes, and performing scientific research all required enormous amounts of computation. Human calculators could complete these tasks, but machines promised to do them much faster. One of the earliest large-scale electronic computers was the Electronic Numerical Integrator and Computer, known as ENIAC. Completed in 1945, ENIAC was enormous. It occupied a large room and contained thousands of vacuum tubes, miles of wiring, and countless electrical components. Yet it represented a remarkable achievement. For the first time, a machine could perform complex calculations using purely electronic processes. Electricity was no longer simply carrying information. It was manipulating it. The development of computers changed how scientists understood electricity. Electrical signals could represent numbers, letters, and instructions. The movement of electrons through circuits could become a form of language. A machine could receive information, process it, and produce a result. The invisible world of electricity had become a world of information. However, early computers had major limitations. Vacuum tubes were fragile. They produced enormous amounts of heat. They consumed large amounts of electricity. Machines required constant maintenance. A single failed component could stop an entire system. The future of computing required something smaller, more reliable, and more efficient. That breakthrough came with the invention of the transistor. In 1947, researchers at Bell Laboratories developed the first practical transistor. The transistor performed many of the same functions as a vacuum tube, but it was far smaller and more reliable. It could switch electrical signals on and off while using much less power. The importance of this invention cannot be overstated. The transistor allowed computers to shrink. Machines that once filled entire rooms could become smaller and more practical. It became one of the foundations of modern electronics. As transistor technology improved, computers became more powerful and accessible. The development of integrated circuits pushed this progress even further. Instead of building circuits from individual components connected by wires, engineers could place many electrical components onto a single piece of material called a chip. The result was smaller, faster, and more efficient technology. The electrical age was becoming the digital age. By the second half of the 20th century, computers began moving beyond laboratories and government facilities. Businesses adopted computers to organize information, manage finances, and improve efficiency. Universities used them for research. Scientists used them to explore problems that would have been impossible to solve manually. Electricity was becoming the foundation of modern information systems. But the most dramatic transformation was still ahead. Computers were about to enter ordinary homes. In the 1970s and 1980s, personal computers began appearing in households. For the first time, Individuals could own machines capable of processing information. Early home computers were simple compared to today's devices, but they introduced people to a new way of interacting with technology. People could write documents, play games, learn programming, and explore digital worlds. The computer was no longer just a tool for scientists. It became a personal device. Electricity had once brought light into homes. Now it was bringing information. The growth of personal computers also changed the meaning of communication. The telegraph had allowed electrical signals to carry messages. The telephone had allowed voices to travel through wires. Computers would eventually allow enormous amounts of information to move instantly around the planet. The foundation for the Internet was being created. Networks of computers began connecting universities, businesses, and eventually households. Information could be stored, shared, and accessed from almost anywhere. The world was entering a new era of connection. Throughout this transformation, electricity remained the hidden foundation. Every computer, every circuit, and every digital device depended on the movement and control of electrical signals. The same force that Franklin studied in thunderstorms and Faraday explored in laboratories was now operating inside tiny electronic components. Electricity had become smaller and more precise. It was no longer only powering machines. It was guiding them. The computer revolution represented a major turning point in the history of electricity. For centuries, humans had used electricity to overcome physical limitations. It helped people see in darkness. It helped machines move. It helped messages travel. Now, electricity was helping humanity think. The invisible current flowing through circuits had become a partner in solving problems, organizing knowledge, and creating new possibilities. The journey from lightning to computers was extraordinary. A force once feared in the sky had become the foundation of the modern world. And yet, even as computers became more advanced, scientists continued searching for new ways to use electricity. The next chapter would explore how electricity became smaller than ever before, entering phones, portable devices, and the technology that now surrounds nearly every moment of daily life. Computers do not understand electricity in the same way humans do. They do not see light bulbs, motors, or appliances. Instead, computers use electrical signals to represent information. A signal can be switched on or off. These two states became the foundation of digital technology. They are represented as the numbers 1 and 0. Together, these simple electrical patterns can create incredibly complex systems. Letters, photographs, music, videos, and entire programs can all be translated into combinations of these electrical states. The idea that electricity could represent information was one of the greatest developments in human history. It meant that knowledge itself could become something stored and moved electronically. The invention of the integrated circuit accelerated this transformation. By placing thousands and eventually millions of tiny electrical components onto a single chip, engineers created devices that were smaller and more powerful than earlier computers. The size of technology began shrinking dramatically. The computer revolution was no longer limited to governments, universities, and large corporations. It was entering homes. During the 1980s and 1990s, personal computers became increasingly common. People discovered that computers could become tools for creativity. They could write, draw, calculate, and explore new worlds. As computers spread, another invention began changing the world: the Internet. The idea behind computer networks had existed for decades. Researchers wondered whether computers could communicate with one another, sharing information across distances. Early networks connected universities and scientific institutions. But over time, These connections expanded. The Internet created a global system where computers could exchange information almost instantly. This represented another major moment in the history of electricity. For centuries, electricity had helped messages travel through wires. The telegraph carried coded signals. The telephone carried voices. The Internet carried something much larger. Entire libraries of information could move through electrical systems. A person could send a message across the world in seconds. They could access knowledge from distant places. They could communicate with people they had never met. The world became more connected than ever before. The development of portable electronics pushed electricity into even smaller spaces. As batteries improved and components became more efficient, technology began leaving the walls of homes and offices. Portable radios, calculators, digital watches, laptops, mobile phones. Each invention represented a new relationship between people and electricity. Electricity was no longer something connected only to buildings. It could travel with us. The mobile phone became one of the most important examples of this transformation. Early mobile phones were large, expensive, and limited, but improvements in electronics allowed phones to become smaller and more powerful. A device that once existed only for making calls eventually became a pocket-sized computer. Modern smartphones combine countless electrical technologies into one small object. They contain processors, memory chips, cameras, sensors, and communication systems. Inside every smartphone are billions of carefully controlled electrical actions happening every second. The complexity is almost unimaginable. Yet the basic principle remains connected to the discoveries made centuries earlier. Control the movement of electricity. Use it to carry information. Create technology. Electricity also transformed entertainment. Music moved from physical recordings to digital files. Movies moved from theaters and discs to streaming services. Photography changed from film to electronic sensors. Games became immersive digital experiences. The same electrical systems that once powered simple machines were now creating entire virtual worlds. The digital age also changed the workplace. Computers allowed people to store and analyze enormous amounts of information. Businesses became more connected. Communication became faster. Entire industries were created around software, technology, and digital services. Electricity was no longer only powering the industrial economy. It was powering the information economy. However, the growth of digital technology also created new challenges. As society became increasingly dependent on electricity, the importance of reliable power systems grew. A power outage could affect communication networks, businesses, transportation systems, and essential services. The invisible infrastructure beneath modern life became more important than ever. The electrical grid had become the foundation of civilization. The digital revolution also changed how humans thought about information itself. For most of history, knowledge existed in physical forms. Books, letters, paintings, maps, documents. The digital age transformed information into something that could be stored, copied, and transmitted electronically. A single device could contain more information than entire libraries of the past. Human knowledge became more accessible than ever before. The story of electricity had come a remarkable distance. Early scientists studied tiny sparks created by friction. They wondered about invisible forces they could barely understand. Centuries later, those same forces were operating inside computers, satellites, and communication networks connecting the entire planet. The electricity flowing through a modern device followed the same fundamental principles discovered by pioneers like Faraday, Tesla, and countless others. The difference was scale. What began as a curious natural phenomenon had become one of humanity's greatest tools. Electricity had evolved from a force of nature into a language of technology. It could create light. It could move machines. It could carry voices. It could store memories. It could connect people. And as the 21st century continued, scientists began exploring even more advanced possibilities. Renewable energy, smart electrical grids, artificial intelligence, quantum computing. The future of electricity would not simply be about producing more power. It would be about using electrical systems in smarter, more efficient, and more connected ways. The invisible current that once fascinated scientists in quiet laboratories had become the heartbeat of the modern world. Electricity had learned to illuminate. It had learned to move. It had learned to communicate. And now it had learned to think. As humanity became more dependent on electricity, a new question emerged. Where would all this power come from? The electrical systems built during the 20th century were designed around large, centralized power plants. These facilities generated enormous amounts of electricity and distributed it outward through networks of transmission lines. For decades, this system worked remarkably well. But the growing demand for electricity brought new challenges. The world needed more energy. At the same time, people began searching for cleaner and more sustainable ways to generate electricity. The next chapter in the history of electricity would focus not only on producing more power, but on producing it differently. The idea of renewable energy was not entirely new. The difference in the modern era was that scientists and engineers learned how to convert these natural forces directly into electricity. One of the most important developments came from improving solar power technology. The idea of converting sunlight into electricity had been studied since the 19th century. Scientists discovered that certain materials could produce electrical currents when exposed to light. This phenomenon became known as the photovoltaic effect. Early solar cells were expensive and inefficient. They were mostly used for specialized purposes, such as powering equipment in space. The idea was simple but powerful. Sunlight could be transformed directly into electricity without burning fuel. A quiet rooftop covered with solar panels could become a small power station. The energy of the sun could flow into homes and electrical systems. Another major source of renewable electricity came from wind power. Humans had used wind for centuries, but modern wind turbines transformed that ancient idea into a new technology. Large blades captured the movement of air and turned it into mechanical motion. Generators then converted that motion into electricity. Modern wind farms could contain hundreds of turbines spread across landscapes or positioned offshore in the ocean. Instead of steam or falling water, the energy came from the wind. Hydroelectric power also continued to play an important role. Large dams used the movement of water to spin turbines connected to generators. The force of rivers became electrical energy. Hydroelectric plants demonstrated one of the most important ideas in electricity generation. Energy does not disappear. It changes form. The movement of water, the rotation of a turbine, the flow of electrons. All were different stages of the same transformation. As renewable energy expanded, the electrical grid itself began changing. Traditional electrical grids were designed around one-way movement. Power plants generated electricity. Transmission lines carried it. Homes and businesses consumed it. But renewable energy introduced a new possibility. Electricity could be generated in many different places. A home with solar panels could produce its own electricity. A community could generate power locally. A wind farm far from a city could provide energy to distant customers. The electrical grid was becoming more complex and more connected. This created the need for smarter systems. The idea of a smart grid emerged. A smart grid uses digital technology to monitor electricity production, distribution, and usage. Sensors and computers help balance supply and demand. They allow power companies to respond more quickly to changing conditions. The electrical grid was becoming not just a network of wires, but a network of information. The relationship between electricity and computers had come full circle. Computers helped manage the very systems that powered them. Another important development was the improvement of energy storage. Renewable energy sources have a unique challenge. The sun does not always shine. The wind does not always blow. Electricity must be available even when the source of generation changes. Batteries became increasingly important because they could store electricity and release it when needed. The development of better batteries also transformed transportation. For more than a century, vehicles had primarily relied on gasoline and internal combustion engines. But advances in electrical technology allowed electric vehicles to become practical. Electric cars used motors powered by batteries instead of engines powered by fuel. They represented another major shift in the relationship between electricity and everyday life. The same electrical principles that powered factories and homes were now moving people. Electric transportation also changed cities. Charging stations became part of the landscape. Transportation systems began exploring new ways to use electricity efficiently. The idea of a future powered by electricity became increasingly realistic. However, the transition toward new energy systems was not simple. Building new infrastructure required time and investment. Electrical systems had to become more flexible. Energy storage needed improvement. Communities had to balance reliability, cost, and environmental goals. The future of electricity would require both innovation and careful planning. Yet the direction of change was clear. For centuries, humanity had searched for ways to control energy. First came fire, then steam, then electricity. Now, the challenge was learning how to use electricity in a more sustainable way. The story of renewable energy represented another stage in humanity's relationship with the invisible force. Early scientists wondered what electricity was. Inventors learned how to create it. Engineers learned how to distribute it. Modern society learned how to depend on it. The next challenge was learning how to preserve the resources that made it possible. Today, electricity is woven into nearly every aspect of human existence. It powers homes, hospitals, transportation systems, communication networks, and the digital world. Yet every flickering light, every charging device, and every electrical signal remains connected to the discoveries of the past. The spark observed by ancient civilizations, the experiments of Franklin, the batteries of Volta, the discoveries of Faraday, the inventions of Edison and Tesla. All of these moments form one continuous story, a story of humanity learning to understand, control, and use one of nature's most remarkable forces. And as technology continues advancing, electricity will remain at the center of the future. The invisible current that changed the world is still flowing, and its story is far from finished. The most remarkable part of modern electricity is not just what it powers. It is how completely it has become part of the background of everyday existence. Electricity has become the hidden foundation beneath modern civilization. Most people rarely think about the enormous systems required to keep power flowing. This network is one of humanity's greatest engineering achievements. The modern electrical grid is often compared to a living system. Every moment of every day, engineers and computer systems balance the supply of electricity with the demand from millions of users. This balance is essential. Electricity is unique because it must usually be generated at the same moment it is used. When someone turns on a light, a power plant somewhere must respond. When millions of people use air conditioning on a hot summer afternoon, the electrical system must handle the sudden increase in demand. Keeping this balance requires incredible coordination. Modern electrical grids rely heavily on computers and digital technology. Sensors monitor the flow of electricity. Automated systems detect problems. Engineers analyze data to predict future needs. The relationship between computers and electricity has become inseparable. The modern world runs on information, and information runs on electricity. One of the most important changes in recent decades has been the growth of data centers. These enormous facilities contain thousands of computers working together to store and process information. The Internet may feel invisible, but beneath it is a physical infrastructure of computers, cables, and electrical systems. The digital world is powered by the same principles discovered by early electrical pioneers. Control the movement of electrons. Transform energy. Transmit information. The scale has simply become unimaginable. Electricity has also transformed medicine. For centuries, doctors relied mainly on observation and simple tools. Modern medicine depends heavily on electrical technology. Medical imaging machines use electrical systems to reveal the hidden structures of the human body. Monitors track heart activity and vital signs. Surgical equipment uses precise electrical controls. Hospitals require constant power because even brief interruptions can have serious consequences. Electricity has become part of the effort to understand and protect human life. The transportation world has also continued its electrical transformation. Electric trains have operated in cities for generations, but recent decades have brought renewed interest in electric vehicles. Advances in batteries, motors, and charging technology have made electric transportation increasingly practical. The idea is not new. The earliest automobiles included electric models. But improvements in technology have allowed electric vehicles to become more efficient and accessible. Electric transportation represents another shift in how humanity uses energy. Instead of burning fuel directly inside a machine, electricity can be generated from many different sources and delivered to vehicles. The same electrical network that powers homes can also move people. Beyond transportation, electricity has changed the way humans interact with their surroundings. Modern buildings are filled with electrical systems that control lighting, temperature, security, and communication. Smart homes can adjust conditions automatically. Sensors can monitor energy use. Devices can communicate with one another. The home is becoming another part of the connected electrical world. This increasing dependence on electricity has also made reliability more important than ever. A century ago, losing power might have meant a dark room and an inconvenience. Today, a major outage can affect communication, transportation, healthcare, and essential services. The importance of maintaining electrical infrastructure has grown alongside society's dependence on it. Engineers continue working to make electrical systems stronger, more efficient, and more resilient. They are exploring ways to protect grids from extreme weather, cyber threats, and increasing demand. The future of electricity will require not only new sources of energy, but also smarter ways of managing the systems already in place. Another major change is the idea of decentralized electricity. For much of the 20th century, electricity flowed in one direction. Large power plants generated energy, and customers consumed it. But renewable energy and advanced technology are creating a more flexible system. Homes, businesses, and communities can now generate their own electricity. Solar panels on rooftops can contribute power to the grid. Battery systems can store energy for later use. Local generation can provide additional support during times of high demand. The electrical system of the future may become more like a network of many connected sources rather than a small number of giant power plants. This represents another major shift in humanity's relationship with electricity. At first, electricity was something people discovered. Then it became something they controlled. Now, it has become something they interact with constantly. It surrounds modern life. It flows through cities. It connects continents. It supports the technologies that define the present. Yet despite its importance, electricity remains mysterious in many ways. The movement of tiny particles too small to see creates effects powerful enough to transform the entire planet. A simple flow of electrons can illuminate a stadium, power a spacecraft, or transmit information across the world. The history of electricity is ultimately a story of humanity learning to work with something invisible. People did not create electricity itself. They learned how to understand it. They learned how to capture it. They learned how to guide it. And they learned how to build a civilization around it. From the first experiments with static sparks to modern electrical grids spanning continents, every discovery added another layer to this remarkable story. The journey of electricity is not only a history of machines and inventions. It is a history of human curiosity. It is a story of people asking questions about the natural world and finding ways to use those answers to improve life. And even now, after centuries of discovery, electricity continues to offer new possibilities. The current that once seemed like a strange force of nature has become the heartbeat of the modern world. It is quiet. It is constant. And it is everywhere. For centuries, humanity has been fascinated by electricity. But even after centuries of progress, the story of electricity is not finished. The future of electricity is still being written. Scientists, engineers, and inventors continue exploring new ways to generate, store, and use this remarkable force. The next chapters of electrical history will be shaped by challenges that are very different from those faced by the pioneers of the past. The question is no longer simply, can we create electricity? Humanity already knows the answer. The question now is, how can we use electricity in smarter, cleaner, and more powerful ways? One of the most important areas of future development is energy generation. For much of modern history, electricity production depended on large power plants using coal, natural gas, or other fuels. But the future of electricity will increasingly focus on finding new ways to produce energy while reducing environmental impact. Renewable energy sources will continue playing a larger role. As these systems become more efficient, they provide new opportunities to generate electricity from natural processes that have powered the planet for billions of years. The challenge is learning how to capture these resources effectively and integrate them into electrical systems. The future grid may look very different from the electrical networks built during the 20th century. Instead of electricity flowing mainly from a few large power plants, future systems may rely on millions of connected energy sources. Homes, businesses, and communities may become both consumers and producers of electricity. This more flexible electrical system will depend heavily on advanced technology. artificial intelligence and computer systems will help manage electricity in ways that were once impossible. Machines will analyze patterns of energy use. They will predict demand. They will adjust power distribution automatically. The relationship between electricity and information will become even stronger. The electrical grid of the future will not only carry energy, it will carry intelligence. Electricity is incredibly useful, but it has always had one major limitation. It must be used when it is generated. Better storage technology will change that. Advanced batteries will allow electricity created during sunny afternoons or windy nights to be saved and used whenever needed. Storage will make renewable energy more reliable. It will help stabilize electrical systems, and it will allow electricity to become even more flexible. The future of transportation will also continue to be shaped by electricity. But electric motors offer a different approach. They are efficient, quiet, and mechanically simple. As battery technology improves, electric transportation will likely become an increasingly important part of daily life. Cars, buses, trains, and even aircraft are all being explored as potential areas for electrical innovation. The idea of moving people through electricity connects directly back to the discoveries of the 19th century. Faraday's simple experiments with magnets and coils eventually became the foundation for motors used around the world. The principles discovered in a small laboratory continue influencing technology generations later. Another exciting area of research is the continued miniaturization of electronics. Electricity has already become incredibly small. Modern computer chips contain billions of tiny electrical components. Future technologies may push this even further. Scientists are exploring new materials and designs that could allow electronics to become faster, smaller, and more efficient. The devices of tomorrow may contain electrical systems far beyond anything imagined today. Artificial intelligence will also depend heavily on electricity. Modern AI systems require enormous amounts of computing power. Behind every intelligent machine are countless electrical operations happening inside computer processors. As artificial intelligence develops, the need for efficient electrical systems will grow. The future of computing and the future of electricity will become increasingly connected. There is also the possibility of entirely new technologies that are difficult to imagine today. Throughout history, many of electricity's most important uses were once impossible to predict. Few people in the 19th century could have imagined smartphones, satellites, or global computer networks. The future will likely bring inventions that seem equally surprising. The history of electricity teaches an important lesson. Progress often begins with simple questions. The pioneers of electricity did not know where their discoveries would lead. Franklin did not know his experiments would become part of a global electrical system. Faraday did not know his laboratory discoveries would power entire civilizations. Tesla did not know his ideas would influence modern technology for generations. They were exploring. They were experimenting. They were following curiosity. And their discoveries changed the world. The story of electricity is ultimately a story about humanity's relationship with nature. Electricity was always present. It existed in storms, in materials, and in the movement of the universe. Humans did not create the force itself. They learned to understand it. They learned to guide it. They learned to use it to improve life. Today, electricity is the foundation of modern civilization. It allows people to communicate instantly. It allows knowledge to spread around the planet. It supports science, medicine, transportation, and technology. It has changed what is possible. and as humanity looks toward the future, electricity will continue to be one of its most important tools. The journey from the first sparks of curiosity to the modern electrical world has been extraordinary. A force once mysterious and frightening has become familiar and essential. It flows silently through wires. It moves invisibly through circuits. It powers the moments that define everyday life. The story of electricity is not just the history of a scientific discovery. It is the story of human imagination. It is the story of people looking at the unknown and asking what might be possible. And somewhere, in laboratories and workshops around the world, new discoveries are already waiting. New inventions, new ideas, new ways to harness the invisible force that has shaped the modern world. The current is still flowing. The lights are still shining. And the story of electricity continues. Tonight, we have traveled through centuries of discovery, curiosity, and imagination. We began with a world illuminated only by flames, a world where candles flickered beside beds, oil lamps guided travelers through dark streets, and fires provided the warmth and light that humans had relied upon for generations. Electricity existed all around humanity, hidden in storms, materials, and the movement of nature. But for most of history, it remained a mystery, a strange force that appeared suddenly in flashes of lightning, a force that scientists could observe but not yet understand. Slowly, patiently, humanity began uncovering its secrets. Ancient observers noticed the strange behavior of static electricity. Experimenters learned how different materials could create electrical charges. Benjamin Franklin looked toward the sky and revealed the connection between lightning and electricity. Alessandro Volta created the first practical battery and gave scientists a steady source of electrical current. Michael Faraday discovered the relationship between electricity and magnetism, opening the door to the generators and motors that would eventually power the modern world. Each discovery was like a small light appearing in the darkness. No single person created the electrical age. It was built by generations of curious minds, each adding another piece to the puzzle. The 19th century brought a new understanding of electricity. The telegraph showed that electrical signals could carry messages across great distances. For the first time, information could move faster than people. A message that once required days or weeks to travel could cross continents almost instantly. The world was beginning to feel smaller. Then came the search for electric light. For thousands of years, humans had depended on fire to push back the darkness. The invention of practical electric lighting changed the rhythm of daily life. The night was no longer something to simply endure. It became another part of the day. Homes, businesses, and cities could remain active long after sunset. Electricity gave humanity control over something that had always shaped life: time. The development of electrical power systems brought even greater change. Thomas Edison helped demonstrate that electricity could become part of everyday life. Nikola Tesla and George Westinghouse helped create systems capable of carrying electricity over great distances. The debate between direct current and alternating current showed that even the future of electricity itself was uncertain. But through experimentation and competition, the foundations of the modern electrical grid were created. Electricity moved from laboratories into streets, from streets into homes, from homes into nearly every part of human existence. The 20th century revealed just how powerful this invisible force could become. Factories were transformed by electric motors. Transportation systems adopted electric power. Communication evolved from telegraphs and telephones into radio and eventually global networks. The home itself changed as electricity brought refrigerators, washing machines, televisions, and countless other devices that reshaped everyday life. Electricity became a quiet companion. It worked behind walls. It flowed beneath streets. It powered the ordinary moments that people often took for granted. Then came the computer age. Electricity learned to carry more than power. It learned to carry information. Tiny electrical signals became numbers, words, images, and sounds. Machines that once filled entire rooms became devices small enough to hold in our hands. The same force that once created simple sparks became the foundation of the digital world. Today, electricity connects billions of people. It powers the internet. It supports medicine and science. It moves transportation systems. It allows information to travel around the planet in an instant. The modern world runs on a network of invisible currents that most people rarely notice. And perhaps that is what makes electricity so remarkable. The most important force in modern life is often the one we cannot see. We do not see the electrons moving through wires. We do not see the signals traveling through circuits. We do not see the countless electrical processes happening inside every device around us. Yet they are always there, quietly working, constantly moving, keeping civilization alive. The story of electricity is not only a story about technology. It is a story about human curiosity. It is about asking questions about the world around us. Why does this happen? How does this work? What could we create if we understood it? Every invention began with someone wondering about something that others overlooked. A spark, a magnet, a strange reaction between materials, a flash of light in a laboratory. Small discoveries became enormous changes. The electricity that powers a modern city began with simple experiments carried out by people trying to understand nature. And the future of electricity will likely begin the same way. With curiosity, with imagination, with someone asking a new question. The next great electrical discoveries may involve cleaner energy, smarter technology, advanced computers, and inventions that we cannot yet imagine. Just as the pioneers of the past could never have predicted smartphones, satellites, or global digital networks, we cannot fully predict where electricity will take humanity next. But one thing is certain. Electricity will continue shaping the future. It will continue connecting people. It will continue powering discoveries. It will continue transforming the way humans live. From the first mysterious sparks to the vast electrical networks of today, the journey of electricity has been one of the most extraordinary chapters in human history. A force once hidden in nature has become the heartbeat of civilization. And now, as the world grows quieter and the lights around us begin to glow, we can appreciate the incredible story behind the simple act of flipping a switch. Because behind every light is a history. Behind every machine is a discovery. Behind every current flowing through a wire is a story of curiosity, persistence, and human imagination. This has been the sleepy history of electricity, a journey through sparks, storms, inventions, and the invisible force that changed the world. Good night.